Dr. M. P. Jayaraman is an assistant professor in mathematics in L.N. Government College, Poneri. He has specialized on geometric function theory. With 14 years of teaching experience, he has handled topics on probability and queuing theory, discrete mathematics, random process, and engineering mathematics. Being a recognized supervisor for guiding PhD and MS students of Anna University, he is the reviewer of the journal Computer Mathematics and Applications. He has also written books on discrete mathematics and has also published papers in 28 international publications, in 4 national publications, and has presented papers in 2 international and in 2 national conferences.
Welcome you all for UGC lecture series in mathematics. In this session, we are going to solve an integer programming problem by making use of Goumerian cutting plane algorithm. So, consider the problem. Solve the integer programming problem. Maximize z equal to x1 plus x2 subject to the constraints 3x1 plus 2x2 less than or equal to 5, x2 less than or equal to x1, x2 greater than or equal to 0 and are integers. By rewriting this LPP into standard form, we will get the first initial iteration is this one. In this one, we already identified that this 3 is our pivot element and we have to convert this 3 into 1 and remaining element in the column as 0. So, in the initial iteration, our entering variable is x1 and leaving variable is s1 and the pivot is 3. So, in the next step we have to convert this 3 into 1 by dividing the entire row into 3. Therefore, in the next table in the place of s1 we have x1 and s2 as it is. The cost of x1 is 1 and cost of s2 is 0. Now, our r1 dash row becomes dividing entire row by 3. Therefore, we have the corresponding xb for x1 is 5 by 3, this will be 1, this will be 2 by 3, this will be 1 by 3 and this is 0. Now, we have to convert the remaining element in the column as 0. Since here already 0 is there, the r2 dash, the new row 2 is the previous row which we have s2 as 2, 0, 1, 0, 1. So, in the next iteration this is our table. Now, we have to check the optimum solution for this table which we display this in the next table. So, our first iteration is this one. Now, again we have to check the optimality for this condition. Here x1 and s2 are the basic variable. Therefore, for x1 zj minus cj value again will become 0. Therefore, no need to compute this one. Similarly, for s2 no need to compute zj minus cj value. Now, for x2 our z2 is 1 into 2 by 3 plus 0 into 1 which we have 1 into 2 by 3 2 by 3 plus 0 into 1 0. So, we have 2 by 3. For s1 our corresponding zj value is 1 into 1 by 3 plus 0 into 0. So, we have 1 by 3. Now, the cost for x2 is 1 and the cost for s1 is 0. Therefore, our zj minus cj value for x1 is 0, for x2 is 2 by 3 minus 1 which we have minus 1 by 3 and for s1 zj minus cj value is 3. So, for the first iteration our zj minus cj for x1 is 0, for x2 is minus 1 by 3, s1 is 1 by 3, s2 0. Here if all zj minus cj greater than or equal to 0, then the optimal solution is obtained. If all zj minus cj greater than or equal to 0, optimal solution is obtained. But as far as this problem concerned, we have z2 minus c2 value is minus 1 by 3 which is negative. Therefore, still we are not arriving the optimal solution. Now, we have to improve the optimal solution. Since only one negative is there, we have to select this variable. Therefore, the variable x2 enters the basis. Entering variable is x2. So, this is our entering variable. Once we fix the entering variable, next we have to compute the ratio xbi by yir. Now, for this problem our xb is 5 by 3 and the corresponding YIR value is 2 by 3. So, we have 5 by 3 by 2 by 3, which is 5 by 2, which is 2.5. Now, for the next one is 2 divided by 1, which is 2. So, among these two value, the minimum is 2, therefore, the corresponding variable S2 leaves the basis. So, in this problem x1 enters and S2 leaves the basis, therefore, the pivot element is 1. So, in the first iteration, our entering variable is x2, our leaving variable is S2 and the pivot element is 1. So, in order to improve the optimum solution, next we have to convert this pivot 1 as 1 and remaining element in that column, that is 2 by 3 as 0. So, the next idea is we have to convert this pivot element as 1. Since it is already 1, our new row R2 double dash is simply R2. So, for R2 we have 2, 0, 1, 0, 1. Next, we have to convert the remaining element in that column, that means this 2 by 3 as 1. How can we convert this 2 by 3 as 1? Now, the R1 double dash, we have to make this element as 1. For that, from this row, that is from R1 dash, if we multiply the R2 dash by 2 by 3, so 2 by 3 into R2 dash, and then if we subtract those things from R1 dash, this term becomes 0. If you multiply this by 2 by 3 and subtract from this one, 2 by 3 minus 2 by 3 becomes 0. Therefore, this entry becomes 0. So, this row is 5 by 3, 1, 2 by 3, 1 by 3, 0. Now, we multiply this row by 2 by 3. Therefore, this will become 4 by 3 and this term becomes 0 and this is 2 by 3 and this is 0 and this is 2 by 3. So, if we subtract, we will get 5 by 3 minus 4 by 3 as 1 by 3, 1 minus 0 1, 2 by 3 minus 2 by 3 0, 1 by 3 minus 0 1 by 3, this is minus 2 by 3. Now, see this 2 by 3 becomes 0. So, by making use of the row elementary transformation, R2 dash as R2 and R1 double dash as R1 dash minus 2 by 3 R2 dash, this pivot element becomes 1 and this 2 by 3 becomes 0, which we display it in the next table as this way. See, the pivot element becomes 1 and remaining element in that column as 0. Next, again we have to check the optimal solution of this table. For that, x in the place of S2, x2 enters, already x1 is there. So, x1, x2 are the basic variable, the corresponding cost are 1. For x1 the cost is 1, for x2 the cost is 1. Now, since x1 and x2 is in the basic, for such basic variable Zj minus Cj value is always 0. Therefore, we no need to compute Zj minus Cj for those basic variable. Now, for S1, the Zj minus Cj value is 1 into 1 by 3 plus 1 into 0, which is 1 by 3 plus 0, which we have 1 by 3. Now, for S2, the corresponding Zj value is 1 into minus 2 by 3 plus 1 into 1. So, minus 2 by 3 plus 1. So, we have plus 1 by 3. Now, the cost for the slack variable S1 is 0 and the cost for the slack variable S2 is 0. Therefore, we have Zj minus Ej is 1 by 3 and 1 by 3. Now, if we observe here, all Zj minus Ej value is greater than or equal to 0. Therefore, optimum solution for this LPP is obtained and the optimum solution is x1 equal to 1 by 3 and x2 equal to 2. Since for this table the optimal solution is x1 equal to 1 by 3 and x2 equal to 2. Now, our restriction on x1 and x2 is x1 and x2 both should assume a non-negative integer value. Our optimum solutions involves x1 and x2 in which x1 takes the value 1 by 3, x2 equal to 2, x2 is an integer, whereas x1 equal to 1 by 3 is not an integer. So, though we obtain optimal solution, the solution is not a feasible solutions. The next idea is, now we have to improve this optimal solution. We have to make this non-negative non-integer solution as integer solutions. For that, we should make use of the Gomerian constraints. So, this optimal solution x1 equal to 1 by 3, x2 equal to 2 should be improved with the help of Gomerian's cutting plane methods. For that, we assume the fractional value of xbi. In this problem, only one xbi has the fractional value, which is 1 by 3. Therefore, for this problem, this is our source row. So, our xb equal to 1 by 3. The corresponding row is called source row. From the source row, we have 1 by 3 equal to 1 into x1 plus 0 into x2, 1 into x1 plus 0 into x2 plus 1 by 3 into s1, 1 by 3 into s1 minus 2 by 3 into s2. So, we have to add the fractional constraint for this problem. For that, the non-integer value is 1 by 3 for x1. Therefore, the corresponding row is called source row. From the source row, we have the value 1 by 3 equal to 1 into x1 plus 0 into x2 plus 1 by 3 into s1 minus 2 by 3 into s3. So, this is our source row. From our source row, we have 1 by 3 equal to 1 into x1 plus 0 into x2 plus 1 by 3 into s1 minus 2 by 3 into s2. So, this is the equation we obtain from the source row. Once we are obtaining the source row, the next idea is, if any of the negative fraction is in the source row, we rewrite the negative fraction as sum of negative integer and non-negative fraction. This fraction is a positive fraction, no need to do anything with that one. Now, if we consider the coefficient of s2, which is minus 2 by 3, is a negative fraction. So, we should rewrite this negative fraction as sum of negative integer and non-negative fraction. Therefore, this equation can be written as 1 by 3 equal to x1 plus 1 by 3 into s1. Now, I will write this as minus 1 plus 1 by 3 into s2. Now, I rewrite this negative fraction as sum of negative integer and non-negative fractions. From this, the Gomerian cut is 1 by 3 s1, 1 by 3 s1, here 1 by 3 s2 is greater than or equal to 1 by 3. So, from the source row we got this equation. From this equation, by rewriting this negative fraction as sum of negative integer and non-negative fraction, we have this equation. From this, Gomerian cut or Gomerian constraint is 1 by 3 s1 plus 1 by 3 s2 greater than or equal to 1 by 3. Now, by multiplying this inequality by minus sign, we have minus 1 by 3 s1 minus 1 by 3 s2 less than or equal to minus 1 by 3. So, multiplying this inequality by minus sign, we will get this equation. Rewrite this inequation constraints into equation by introducing a slack variable, which will write it as minus 1 by 3 s1 minus 1 by 3 s2 plus gs equal to minus 1 by 3. Here this gs is called Gomerian slack variable. So, by introducing a Gomerian slack variable in this equation, we will get the Gomerian fractional cut as minus 1 by 3 s1 minus 1 by 3 s2 plus gs equal to minus 1 by 3. Now, we should attach this Gomerian constraints in the optimum simplex table and solve the resulting LPP using dual simplex method. So, now in order to convert the non-integer optimum solution as an integer solution, first we have to construct a Gomerian constraint. For this problem, our Gomerian constraint is minus 1 by 3 s1 minus 1 by 3 S2 plus GS equal to minus 1 by 3. Now, by attaching this Gomerian condition in the bottom row of the simplex table obtained in the second iteration and solve the resulting integer programming problem with the help of dual simplex method will improve the optimal solutions. Let us have a break. Welcome back. Before break, we obtained the Gomerian cut or Gomerian fractional cut for the given problems. Now, by adding that Gomerian constraints in the bottom row of the above optimal simplex table, we will get a new table and we solve the resulting IPP using dual simplex method. So, this is the optimum simplex table we obtain as a solutions. Now, with this optimal simplex table, if we add that Gomerian constraints, which is minus 1 by 3 S1 minus 1 by 3 S2 plus GS equal to minus 1 by 3. Now, we should add this Gomerian constraints in the bottom row of the simplex table. Therefore, the next row is corresponds to Gomerian slag. So, our basic variable is Gomerian slag. The corresponding cost value is 0. Now, the xp value, which is the right hand side of this Gomerian constraint, which is minus 1 by 3, which we will rewrite here as minus 1 by 3. Then in the Gomerian constraint, the coefficient of x1 is 0, x2 is 0. Therefore, here we have 0, here we have 0, and the coefficient of s1 is minus 1 by 3. Corresponding to s1, we will write minus 1 by 3, and coefficient of s2 is minus 1 by 3. We will write it as minus 1 by 3, and that Gomerian slag, the corresponding coefficient is 1. So, by adding this Gomerian constraints in the previously obtained optimum simplex table, we will get the new table which we displayed here. Now, we have to improve this solution to an optimum integer solution. For that, we have to use dual simplex method. For dual simplex method, first we have to look into the all xbi value. If all xbi value is positive and all zj minus cj greater than or equal to 0, then optimal solution is obtained. For this problem, x1, x2, gs in the basic, therefore, the corresponding zj minus cj value for those variable is simply 0. Therefore, no need to compute zj minus cj value for those variables. Now, for s1, the zj minus cj value is 1 into 1 by 3 plus 1 into 0 by 3. So, which we have 1 by 3. Then for S2, 1 into minus 2 by 3, 1 into minus 2 by 3 plus 1 into 1, 1. So, we have minus 2 by 3 plus 1. So, which we have 1 by 3. The corresponding cost value for S1 is 0 and S2 is 0. Therefore, Zj minus Cj value is 1 by 3, 1 by 3. So, here all Zj minus Cj greater than 0, but if you observe the xbi, the xbi for gs is negative, which is minus 1 by 3. So, which clearly shows that for this problem our leaving variable is gs. So, this is our leaving variables. Once we identify leaving variable in dual simplex method, our next step is to identify the entering variable. In order to identify the entering variable, we have to compute the maximum value of zj minus cj by ykj. That ykj value should be strictly less than 0. So, in order to fix the entering variable, we have to compute maximum zj minus cj by ykj, ykj less than or equal to 0. Now, in this row, the ykj which is negative is minus 1 by 3, minus 1 by 3. Therefore, if we compute this value for this table, for this S1 which we got our zj minus ej value is 1 by 3. So, 1 by 3 by minus 1 by 3. Next, for zj minus ej value for S2 also we got it as 1 by 3. So, zj minus ej for S2 is 1 by 3 and corresponding ykj is minus 1 by 3. So, in order to fix the entering variable for this table, we have to compute maximum of zj minus cj by ykj, where ykj less than 0. So, in this row the negative Yk value is this one. So, for S1 and S2, if we compute this ratio, we will get this one, which is minus 1 minus 1. So, maximum minus 1 1, which is minus 1. So, here the maximum values occurs in both cases for S1 and S2. Therefore, we can arbitrarily choose the entering variable. I will choose the x1 as my entering variable. So, for this problem, that maximum values occurs in two places for S1 and S2. So, in order to fix the entering variable, we can choose arbitrarily any one value. I will choose x1 value. So, for this problem, my entering variable is S1. So, in this problem, our leaving variable is GS leaves the basis and S1 enters the basis. So, our next step is we have to convert this pivot element minus 1 by 3 as 1 and remaining element in that column as 0. So, in the next step our aim is we have to convert this minus 1 by 3 as 1 and the remaining two element in the column as 0. It is already 0, therefore, no need to do any row operation for this one, and we have to convert this 1 by 3 into 0. So, my next aim is I have to convert this minus 1 by 3 as 1. For that, I have to, my R3 dash is nothing but minus 3 R3. So, if you multiply the entire row by minus 3, this term becomes 1. Therefore, for this one minus 3 into 1 by 3, which will have 1. Then for this one 0, 0. If I multiply by minus 3, it will become 1. It will become 1. If I multiply by minus 3, it will become minus 3. So, this pivot element 1 by 3 becomes 1. We have to convert the remaining element in the column as 0. Since it is already 0, my R2 dash is simply R2, which we have 2, 0, 1, 0, 1, 0. Next, my aim is I have to convert this element 1 by 3 as 0. In order to convert this element 1 by 3 as 0, the row operation is our R1 dash is from the row R1, if we multiply this row by 1 by 3 R3 dash and subtract it, this term will become 0. So, this row is nothing but 1 by 3, 1, 0, 1 by 3 minus 2 by 3, 0. If you multiply this row by 1 by 3, it will become 1 by 3, then 0, 0, 1 by 3, then it will become 1 by 3, 0. So, our next idea is convert this pivot element as 1, this element as 0 and this element as 0, which we got it as the next table. See, here the pivot element becomes 1, remaining element in that column is 0. Now, we have to check the optimal solution for this problem with the help of dual simplex method. Since x1 is in basic, no need to compute Zj minus Ej value for this one, and x2 is in the basic and S1 is in the basic. Now, for S2, our Zj minus Ej value is 1 into minus 1 plus 1 into 1, which is minus 1 plus 1, it will become 0. Now, for Gs, 1 into 1 plus 1 into 1, which will become 2, and this cost will become 0. Therefore, for S1, for S2, 1 into minus 1 plus 1 into 1 plus 0 into 1 becomes 0. For Gs, 1 into 1 1 plus 1 into 1 1. So, 0 into minus 3 0. So, 1 plus 1 plus 0, which we have 2. The corresponding cost value for S2 is 0 and Gomeryan slack is 0. So, here we will got all Zj minus Ej greater than or equal to 0, and if we observe that xb, all xbi are non-negative and also takes an integer value. So, in this problem, since all Zj minus Cj greater than or equal to 0 and all xbi value are non-negative and integer, optimum solution to the problem is obtained. Since all Zj minus Cj greater than or equal to 0 and all xbi are non-negative and all xbi are integer, optimum solution to the given integer programming problem is obtained. The optimal solution is x 1 equal to 0 and x 2 equal to 2 and the slack variable s 1 equal to 1. So, in this problem the optimal solution is x 1 value equal to 0 and x 2 value equal to 1. Since for this problem our objective function is maximum z equal to x 1 plus x 2, by substituting this x 1 x 2 value in this objective function, the optimum solution to the given problem is x 1 0, x 2 2 and maximum z equal to 2. So, the optimal solution to the given problem is x 1 0, x 2 2 and maximum z equal to x 1 plus x 2 which is 0 plus 2 which is 0. So, the optimal solution to the given problem is x 1 0, x 2 2 and maximum z equal to 2. Now, the optimal solution to the given integer programming problem is obtained. Now, we go for the geometrical interpretation of the given integer programming problem, in which the given constraint to the problem is 3 x 1 plus 2 x 2 less than or equal to 5 and x 2 less than or equal to 2. So, already we discussed for the given problem the Gomerian slack is 1 by 3 s 1 plus 1 by 3 s 2 greater than or equal to 1 by 3. So, already we obtained the Gomerian constraint for the given problem is 1 by 3 s 1 plus 1 by 3 s 2 greater than or equal to 1 by 3. The given constraint for this problem is 3 x 1 plus 2 x 2 less than or equal to 5, x 2 less than or equal to 2. Now, by introducing a slack variable for this problem, this inequation becomes 3 x 1 plus 2 x 2 plus s 1 equal to 5. Now, by introducing slack x 2, this equation can be written as x 2 plus s 2 equal to 2. So, from this equation we have our s 1 value as 5 minus 3 x 1 minus 2 x 2, and from this equation our s 2 equal to 2 minus x 2. Now, by substituting this x 1 x 2 in this Gomerian constraint, our Gomerian constraint becomes 1 by 3 into 5 minus 3 x 1 minus 2 x 2 plus 1 by 3 into 2 minus x 2 greater than or equal to 1 by 3. Now, by cancelling this 1 by 3 and by simplifying this equation, the simplification of this equation is minus 3 x 1 minus 3 x 2 plus 7 greater than or equal to 1. So, we will rewrite it as minus 3 x 1 minus 3 x 2 greater than or equal to minus 6. Now, we rewrite this equation as 3 x 1 plus 3 x 2 less than or equal to 6, which gives us x 1 plus x 2 less than or equal to 2. So, from the given set of constraints and from the Gomerian constraint, we will get our new equation as x 1 plus x 2 equal to 2. We will represent this geometrically. What we have is this one. Now, our first equation is 3 x 1 plus 2 x 2 equal to 5. By taking x 2 equal to 0, our x 1 equal to 5 by 3. So, I will take my 5 by 3 here. So, this is one point 5 by 3 comma 0, and from the equation we will take x 1 equal to 0, we will get x 2 equal to 2.5. So, this is the first constraints, 3 x 1 plus 2 x 2 equal to 5. The second equation is x 2 less than or equal to 2. So, we have this is 2.5, we will take this as 2. So, this is the equation x equal to 2. So, the solution space for this problem is this one. This is the solution space. Now, from the Gomerian constraint, we will got a equation x 1 plus x 2 equal to 2. If we draw this equation, which is a line joining the points 2 comma 0 and 0 comma 2. So, we got this equation as this way. So, this is the line x 1 plus x 2 equal to 2. So, our Gomerian constraints reduce the solution space from the original solution space is this one. From this it reduce the solution space as this way. So, this is a geometrical interpretation of the given integer programming problem, in which we have solution as this is the point 2 comma 0 and this is the point 1 comma 1. So, we have two kind of solution, x 1 equal to 1, x 2 equal to 1 and maximum z equal to 2, and another solution is x 1 equal to 0, x 2 equal to 2 and maximum z equal to 2. So, from this geometric interpretation it is clear that the Gomerian constraints terminate the solution space, it reduces the solution space each and every time. The question for exercise is maximize z equal to 2 x 1 plus 2 x 2 subject to this constraints. So, with the help of Gomerian algorithm we can solve the given integer programming problem. Thank you.